Uh, Hello, welcome to my new lecture. Today we'll be looking at Shor's algorithm. Um, First, we have to check what is Shor's algorithm. Okay, the Shor algorithm was developed by Peter Shor, which is a mathematician and also a computer scientist in 1994. And this algorithm have the capability of to factoring a large prime number in a polynomial time. But here it requires a quantum computer to do that. The algorithm shows in principle that quantum computer is capable of factoring very large number in polynomial time. All right. So briefly, this is what is known as Shor's algorithm. Now, what is the Shor's process? The algorithm consists of two parts. Okay. Um, First is a change of the problem from factor to order finding the period. What we mean here is that conversion of the problem of factoring to the problem of finding a period. So this can be done using our classical computers that we use nowadays. And the second one, which is solving the order, that is finding a problem, that is quantum period finding. So here um, it means that the finding the period, okay, finding the period, that is quantum period finding using the quantum Fourier transform, and it is responsible for the quantum speedup. What I mean here is that the Fourier transport, quantum Fourier transport is the one that helps in speeding up the quantum processes in using quantum computers. So the problem the problem change portion, that is the first one there, can be done on a traditional computer, that is the ordinary classical computers that we have now. But the second part of it, that is the order of finding portion, that requires what? Quantum computers. Now, Shor's algorithm. First, we have to formulate a problem in order for us to easily explain what is Shor's algorithm. First, the problem is as given an odd composite number n, find an integer d that is strictly between n and that divide n. So what we mean here is that we are given any composite odd number, okay, very big number, and then we are asked to find an integer d, and which integer d must be less than n and but greater than 1, and secondly it must divide n. So in this presentation we will be breaking the algorithms into series of steps in order to show how the above problem can be solved using it. So that is how I break it into series of steps. So the first step here is that you can easily pick any number, any integer a, okay, that is less than n, such that they are co-prime to each other. After that, when we say co-prime, that is either one of the a or n is a prime number. Maybe the other one may be an ordinary odd number. Then, step 2, find the GCD of the two integers. Here, the GCD can be calculated either using any available algorithm, for example, the Euclidean algorithm. Then, if the GCD is found to be 1, it's not 1, then there is a factor of n. Now, for example, if we take an n to be 9, just small for example, for sake of understanding, if n is 1 and we now randomly pick a to be like 3, then if we are to find the GCD of 9 and 3, then definitely the GCD will be more than 1, because 3 can divide 3 and 3 can divide 9. So therefore the GCD of 3 is 3 there. So therefore there exists a factor in 9. So therefore in this stage the algorithm is finished. But what about if the GCD is 1? In that case, we use quantum computer to find the unknown period p of the given function f of x equals to a to the power of x mod n. The fifth step here is that, because in the previous function, when you are to find the p, then that p may be either even or odd. So if it is even, if it is odd number, if the integer p is odd, then we have to go back to step 1 and start it afresh again. But if the p is even, then we can move to the step 6. Since we understand that p is even, in this step we have to compute this expression, that is 8 power of p divided by 2 minus 1 into 8 power of p divided by 2 plus 1, which is equals to 8 power of p minus 1, which is equals to 0 mod n. So if this expression holds, that means if 8 power of p divided by 2 plus 1 equals to 0 mod n, then we have to go back to step 1, because there exists a trivial solution in this stage. But if the a to the power of p divided by 2 plus 1 is not equals to 0 mod n, then we have to go to next step, which is step 7. There in step 7 we compute d, which is equals to GCD of a to the power of p divided by 2 plus or minus 1 comma n. So we find the GCD. When we find the GCD, then we have the d. We exist with the answer d, and the algorithm is finished. So this is about the algorithm. What about the running time? The algorithm's running time is big O log n to the power of 3. This means when solving 3 quantum problem in a given time of big O log n each, then the runtime for the algorithm would be big O log n cubed. So this is superposition function. This function as a quantum transform and quantum Fourier transform, because the algorithm is derived from the quantum Fourier transform. So with this we have come to the end of brief explanation of Shor's algorithm. Please, if you like this video, kindly click the like and subscribe button down there for my next videos, please. So thank you.